Hi guys, we're going to talk about molecular geometry, VSEPR theory, and how to NASL. So here we go. I'm going to go through the examples with you at the top of your VSEPR theory or your VSEPR practice assignment. You do not have to do the examples in the assignment to get credit for the assignment. The examples I recommend you follow along with so that you know what you're doing, but you do not have to do the examples at the top of your assignment to get credit. So let's talk about molecular geometry. So molecular geometry refers to the fact that elements are actually 3D and not two-dimensional as they're drawn on paper with Lewis dot structures. Lewis dot structures are basically just ways that we draw atomic models of different molecules and compounds showing the number of lone pairs and bonds they have. They give you a general idea of what the molecule should look like. VSEPR theory stands for valence shell electron pair repulsion. The valence shell part refers to the atoms that are going to be involved in bonding, and repulsion refers to the lone pair electrons that are going to repulse each other or push them into the shapes of the molecule. There are different shapes for VSEPR theory, and we'll talk about what those different shapes are. But the one thing you need to be able to tell me, or that you need to understand, is what regions of electron density mean. Regions of electron density, if you look at this picture in the corner, refers to bonds and lone pairs. A double bond is still just one region. Okay, so this one only has two, even though it's two double bonds. This one has 1, 2, 3, because we're looking at the central atom, 1, 2, 3. And this one has 1, 2, 3, 4. This can also refer to lone pairs on the central atom, and we'll talk about what all of that means when we start drawing these in a minute. So there are several shapes, and we're going to go through these shapes really quick. Put me up here in the corner. The first shape is linear. Linear has two areas of electron density. So there's going to be two things bonded to the central atom. It has 0 lone pairs on the central atom. Lone pairs we're talking about here is on the central atom. And it has a bond angle of approximately 180 degrees. So it's going to be in a straight line. Your next shape is trigonal planar. Trigonal planar is going to have 3 areas of electron density on the central atom. So it's going to be 3 things bonded to the central atom with 0 lone pairs on the central atom, and it's going to have a bond angle of approximately 120 degrees. Bent or angular. Now there are 2 bent or angular, but the first one is going to have 3 areas of electron density, and that's going to be 2 things bonded with 1 lone pair. So you have, and this is on the central atom only. If you'll notice, there's 1, 2, 3, 4, 5, 6 lone pairs on this molecule, but we're only focused on the central atom. And it's going to have a bond angle of less than 120 degrees. Tetrahedral has 4 areas of electron density. There's going to be 4 things bonded to the central atom with 0 lone pairs in the central atom with a bond angle of about 109 degrees. Trigonal pyramidal is going to have 4 areas of electron density, similar to tetrahedral, only the fact that one of those areas is going to be a lone pair with a bond angle of less than 109 degrees. Bent or angular number 2 has 4 areas of electron density, but 2 of them are lone pairs on the central atom with a bond angle of much less than 109 degrees. So when we draw Lewis structures for covalent compounds, we can do it using NASL. NASL stands for needed, available, shared, and lone pairs. It's going to help you determine how to draw your shapes. So we're going to draw lines to depict your shared or bonded electrons, and 2 dots to represent your lone pairs. And you can check these by counting your octets, and we'll learn how to do this together. So for N, needed, all atoms need 8 electrons to fill their octet, except for hydrogen that needs 2 and boron that needs 6. Those are your only 2 exceptions. A is available. This is the sum of all the valence electrons. So that's looking at these numbers that I've written in red across the top here. S is for shared. To find that, you're going to do N minus A, and that's going to be shared. And then when you divide that by 2, it gives you the number of bonds. And L is lone pairs. That's A minus S divided by 2 for lone pairs. So when we draw NASL, you're going to determine the number of bonds needed and draw your skeletal structure. You have to figure out what your central atom is, and normally it's your least electronegative atom, so the atom furthest from fluorine on the periodic table. If it's carbon, carbon will be your central atom. If it's hydrogen, hydrogen's never going to be your central atom. If it's two atoms, then you don't have a central atom. They're both going to be bonded to each other. Okay? But carbon is generally, if it's in a formula, carbon is generally your central atom. You're going to connect all your atoms using the number of bonds, and then you're going to make sure everybody has an octet, and that's how you're going to figure out where your lone pairs go. For polyatomic ions, these are the ones that have charges. If it's a negative charge, we're going to add to our available, because remember, electrons are negative. So negative, we're going to add to available. Negative, we're going to add to available. And positive, you're going to subtract from available. So let's go ahead and now you're going to do this assignment in Cami, and I get that your drawings aren't going to be super beautiful, and I'm 100% okay with that because my drawings are about to be not beautiful. I'm going to make my face smaller. I'm smaller now. Okay, so we're going to go ahead and do this, and we're going to hope for the best. All right, so N stands for needed, so all need 8. And how I set this up is I'm going to do each atom individually in the order. So I'm going to start with N. I have 1 N, and I need 8 of those. Plus, I have 3 H's, and I need 2 for each of those to fill their octet. So 8 plus 6 is 14. I'm really hoping my math is right today. Available stands for the number of valence electrons. So if we look at nitrogen, which is right here, it has 5 valence electrons. So I have 1 nitrogen with 5 valence electrons plus 3 hydrogens, and all hydrogens have 1 valence electron. I know my handwriting is really pretty. So that's going to make 8. All right, shared is going to be N minus A, so 14 minus 8, which is 6. I divide that by 2. That's going to give me 3 bonds. All right, for lone pairs, I do S or A minus S, so 8 minus, and it's this number here before we divide by 2. 8 minus 6, which gives me 2. And then divide that by 2. That's going to give you 1 lone pair. So let's go ahead and draw it now. Okay, so my central atom, it's never going to be hydrogen, so it's going to be nitrogen. And I'm going to have 3 bonds coming off of nitrogen. And that works out really good because look, I have 3 hydrogens. All right, and then I have 1 lone pair left. So I need to make sure the octet for everything is met. When I look at bonds, bonds are worth 2 electrons. So hydrogen only needs 2. So this one has 2, this one has 2, this one has 2. So 2, 4, 6, nitrogen needs 8. So I'm going to put my lone pairs on nitrogen. So then the shape of this is going to be trigonal planar. I don't know if I can write that. Trigonal. Oh, super pretty handwriting. So trigonal planar. That is my first shape. So I'm going to give you just a second so we can look through this, and we'll talk through how we got this in just a second again. I'm actually double checking that I told you the right shape name. I did. It's trigonal planar. And the reason why I know it's trigonal planar is I have 4 areas of electron density. I have 1 bond, 1 bond, 1 bond, lone pair. So it's 1, 2, 3, 4. And then I have 1 lone pair on the central atom. So that's how I know it's trigonal planar. Oh, I lied. It's trigonal pyramidal. It's trigonal pyramidal. My bad. Trigonal pyramidal. That's why I checked my work. There we go. All right, so again, N is your number of valence electrons needed. Everyone wants 8 except for hydrogen that wants 2. A is number of valence electrons. We find that by looking at the periodic table. S is N minus A, and L is A minus S. Okay, so let's erase this and do the next one. All right, next one is CCl4. So now we're gonna do the same thing again. I have one carbon and it needs 8 valence electrons plus 4 chlorines that need 8 valence electrons. So 8 times 5 is 40. All right, carbon is located right here on the periodic table. It has 4 valence electrons. And then I have 4 chlorines, and they each have 7 valence electrons. So 4 times 8 is a number, 32. All right, shared. So S is N minus A, so 40 minus 32, which gives me 8. I'm going to divide that by 2 to get my number of bonds, which is 4 bonds. Okay. L is A minus S, so 32 minus 8, which I do believe is 24. Okay. And I divide that by 2 to get my number of lone pairs. So 12 lone pairs. So now we're going to do my drawing. I told you before, if I have chlorine, he's probably going to be my central atom. And that's true in this case. And then I have 4 bonds. So I'm going to draw 4 lines off of chlorine. Or carbon, sorry. 4 lines off of carbon. And I'm going to put a chlorine on each one. So I still have CCl4. When you're doing your drawings, you need to make sure your drawing matches up with what you put over here. So I have a carbon, I have 1 carbon and 1, 2, 3, 4 chlorines. I can't have extra, I can't have not enough. I have to have the same thing as the formula. So now for lone pairs, if I look at carbon, it has 2, 4, 6, 8. Its octet is already met. Chlorine, each chlorine only has 2 because each one only has a bond, or 1 bond, and they need 8. So if I take 12 and divide it by my 4 chlorines, each one's going to get 3 lone pairs. And that is going to equal my 12 total lone pairs. So the shape on this one, I have 4 areas of electron density on the central atom, 1, 2, 3, 4, 0 lone pairs on the central atom, so that means the shape is tetrahedral. So that's how you do the next one. All right. Now we have H2CO. I really like this example because for one thing, it's not as obvious what your central atom can be. Now we know that it's going to be carbon because if I have a carbon, it's usually my central atom. But we now have 3 different atoms we're working with instead of just 2 like we've been doing before. So again, N again is need. So how many do I need in its shell? I have 2 hydrogens that each need 2 to make an octet. I have 1 carbon, it needs 8. And I have 1 oxygen, it needs 8. So 4 plus 16 gives me 20. Okay. A available is how many valence electrons do I have? We already have discussed that hydrogen, I have 2 hydrogens and they each have 1 valence electron. Carbon again has 4 valence electrons and I have 1 of those. And then oxygen has 6 valence electrons and I have 1 of those. So I have 12 available. Okay, S is N minus A, so 20 minus 12, which gives me 8. Divide by 2, I get 4 bonds. All right, 12 minus 8, because I'm doing A minus S, and it's the S before it divides by 2, is 4. Divide by 2, Gives me 2 lone pairs. All right, my central atom is going to be carbon. Now this is a little bit different this time. I have 4 bonds, but I only have 3 atoms to attach. So the hydrogens are obvious that they're going to get 1 bond because they only need 1 to complete its octet. It's 2, 2, okay. Well, and then I have an oxygen and I have 2 bonds left. I can do what's called a double bond. That means carbon and oxygen are going to share it. And I know that I can do this because I know double bonds exist. Single, double, and triple bonds exist in covalent compounds. And I am going to do this, and when I do that, I have 2, 4, 6, 8 on carbon, so its octet's met. I still have 2 lone pairs left, and we know that hydrogen has its octet met, but oxygen only has 2, 4. Now I have 6, 8. Its octet is met. So now we need to come up with what shape this is. I have 3 areas of electron density on my central atom. I have 1, 2, 3. A double bond counts as only 1 area of electron density. 0 lone pairs on my central atom. So this one is actually trigonal planar this time. All right. And then let's do our last example on here. This last one is a polyatomic ion, and I did this on purpose because if you remember, our special rule for polyatomics is if it has a negative charge like this one does, we're going to add to our available. Also, when you draw polyatomics, your final drawing will have the molecule in brackets, which are like the square parentheses, with the charge written on the outside. Let's go ahead and do this one. So I have S, I have 1S, and it needs 8. Plus my 3 O's that also need 8. I promise that's a 3. So 8 times 4 is 32. All right, I have 1 sulfur, and it has 6 valence electrons. And then I have 3 oxygen, and it also has 6 valence electrons. And then I'm taking my 2 and I'm adding it because it's negative. Because remember, electrons are negative. So I have 6 times 4 plus 2 gives me 26. And then everything else is still the same for your NASL. So S is N minus A. Which is 6. I'm going to divide by 2. I get 3 bonds. And then I'm going to do A minus S, so 26 minus 6 is 20. Whoa! Divide by 2 is 10 lone pairs. That O is very aggressive. My bad. Or 0 was very aggressive. All right, so now I'm going to draw my central atom. I have 1 sulfur, so we're going to put that guy in the middle. All right, I have 3 bonds and 3 oxygens. So 1, 2, 3. And it doesn't matter where you draw these connected to the central atom. I could have drawn one up here if I wanted to, but I didn't. All right, and then I have 10 lone pairs. So let's look at sulfur. I have 2, 4, 6, 8. Oxygen, I have 2, 4, 6, 8. Oxygen, I have 2, 4, 6, 8. 2, 4, 6, 8. 3, 6, 9, 10. All right, now the shape, we've seen the shape before. I have 4 areas of electron density on my central atom. 1, 2, 3, lone pair makes 4. And 1 lone pair on my central atom. That means it's trigonal pyramidal. And if you remember what I said about the polyatomics, when I draw them, I finish drawing them by putting them in brackets and writing the charge on the outside, which is a -2 or 2 minus. So there you go. So that's how we do NASL and VSEPR. I think this is a great way to draw covalent compounds. It's a lot easier than how I originally learned it, which was where you just basically kind of guess how everything goes together. This has a little bit of math involved that's not real complicated. It allows you to draw these Please message me if you have questions. Refer back to this video. There are lots of ways to draw these, but I recommend that we do them via NASL. Good luck, and please message me if you need help. I'll talk to you later. Bye.